All right, I think I'm online. I hope everybody can hear me, although I don't know where the back channel is, but we'll see. So, the last couple of days we had very interesting talks about deep in technical exploitation techniques and some more broader ethical notions of security and ethical computing. Now, this talk is more about giving a little bit of background on a very recent and very important development in cryptography that will affect pretty much the entire IT sphere, and that is post-quantum crypto. First things first, I'm going to introduce myself real quick. Not because I like talking about myself, just so you know who's talking to you. I'm a security researcher and trainer at the German-based security company called Neodyme, and I spent most of my time looking at other people's code and finding vulnerabilities there. And my specialty in this is finding bugs and pawning them in crypto code or code that employs cryptography. And as we'll see later, that's pretty much all code these days. I also sometimes speak at conferences and I do trainings. For example, at the DEF CON trainings events, I talk about doing crypto right and using cryptography right and how to exploit poor usage of cryptography. On the side, I'm trying to finish my PhD at the MPI, where I work on implementation of post-quantum cryptography. During my studies in my bachelor and master, I did a lot of CTFs, capture the flag competitions, like we have seen here at this conference, the Battle CTF. So there I was a finalist at the big competitions like DEF CON CTF or Google CTF or Hackasat, which is the US Air Force CTF for hacking satellites, which was a lot of fun. So enough about me. We are here to talk about cryptography. So if you have a client and a server, or two clients or two servers, just any computers that talk to each other, nowadays, most likely, they will be using some sort of cryptography to guarantee their confidentiality, but also their integrity and authenticity of their messages. So whenever you talk to, I don't know, this website, because you're watching this stream, you do use the common protocol stack, most likely Ethernet, then IP, then TCP, but on top you will use TLS, which is a cryptographic protocol. So almost all digital communication these days is secured using cryptography. So if you use a tool that uses a network connection, like SSH or VPNs or whatever, they will be using cryptography, but also normal software like your browser or your app on your phone will use cryptography to secure its communication. So yeah, if you use a computer, you use cryptography if you want, if you like it or not. But actually, computers are much more ubiquitous these days. They're really everywhere. So what does that mean? Well, cryptography is everywhere because computers are everywhere. So if you unlock your car with a remote, or if you open a door to your office with a fob like that, they will be using cryptography. If you use a credit card or a debit card, there's a small chip, Cortex-M processor, that will perform cryptographic operations to sign your transactions. Modern passports We use paid protocols. The electricity counter in my basement has a public key and uses cryptography to transmit its usage statistics. So cryptography is really everywhere because computers are everywhere. So its difficulty stays to enter a room without there being any cryptography present in this room. And that's problematic because for most people, cryptography is just witchcraft because they don't think it's relevant to them. They think it's something some cryptographers do, but not them. And then when people do things but don't really understand what they're doing or using, at least that leads to bugs. And bugs lead to exploitable vulnerabilities, as you all know. So there's a big mismatch, and one way to address this is to bring cryptography more into the applied security sphere so people get aware of what that actually is and how to use it properly. But we're going to do something else now. We're going to look at a very fundamental problem that cryptography has right now. You might not be able to exploit it because you would require a very, very special kind of computer, but it's still a big topic of today's InfoSec world. So I talked about cryptography, that it's everywhere, everyone uses it. You use it right now to watch this stream. But what is cryptography? Cryptography is made up roughly on a high level of two things. One is primitives and one is protocols. A primitive is a sort of building block that you can use to accomplish something. For example, to accomplish confidentiality. You would use a cryptographic primitive, namely encryption. For example, AES encryption. And that's if you want to do something very specific. But if you actually have a protocol, if you want to talk to somebody else, if your computer wants to do something, one primitive is not enough. You have to combine primitives into a sort of protocol. So cryptographers design primitives on one hand. These are building blocks to do something, for example, to encrypt something or to sign something. But cryptographers also design protocols that combine those primitives into a way that an application developer can use. This is also a common misconception since we're talking about bugs. Very often, application developers think they can just use a primitive to do something. Very often, primitives break really fast if you violate assumptions. That's why it's so important to use a primitive only within a protocol. So a primitive is not a protocol. Just because you use AES GCM doesn't mean you can do secure network communication, right? It's a primitive, not a protocol. So if you have a product, let's say you're using the Signal messenger, which is a pretty good messenger for private communication. What you're actually using down on the wire is Signal protocol, which it was an invention, let's say, based on other techniques from other people of the Signal Foundation. And this Signal protocol internally makes heavy use of different primitives. For example, one primitive they use is called the curve 25519. Some of you might have heard this name before. It's an elliptic curve-based primitive that can give you key exchange mechanism, but can also give you a mechanism to authenticate yourself to somebody else or somebody else authenticating themselves to you. So a cryptographic primitive is something like an encryption algorithm or a signature algorithm or a key exchange algorithm. They are very often misused in practice, these primitives, as I said, when I do code audits or when I look through other people's codes, very often that's the problem. They just use a primitive and the primitive itself is secure, but they use it in a wrong way, or they use it in a wrong technical context, and then it becomes exploitable. So if you use Signal, you actually use the Signal protocol, which is just a definition of events, a state graph, if you will, that defines if this message arrives, you do this message, yada, yada, yada. So protocol is just a sequence of messages in combination with cryptographic primitives. The most widely used protocol, cryptographic protocol, is probably TLS, which you use, for example, for web browsing. But Signal protocol is also pretty out there. I mean, a lot of tools are using it. For example, WhatsApp Messenger also uses the Signal protocol. So what all of these protocols, like Signal protocol or TLS or VPN solutions like WireGuard or IPsec, what they all have in common, these protocols, is that they, on a very high level, work in 3 steps. So first, each side of the communication gathers entropy because randomness, because you need random keys. The keys are not random enough, and also there, very often, developers make mistakes. But if keys are not random enough, nothing works. So they gather entropy to have strong randomness. Then they establish a symmetric key by using asymmetric cryptography. And then they use symmetry to actually encrypt and authenticate the data that they exchange. So here in the 3rd step, the actual being sent, like your request to the web server, for example. And a crucial step here, I mean, they're all crucial, but the most crucial step is the second one. Because in the 2nd step, we use asymmetric cryptography. Alice knows she's really talking, Bob knows he's really talking to Alice. And they agree on a key. And somebody who's in the middle, a man in the middle, can't just key. So asymmetry is very, very important in information security. So back to this original picture of TLS. It's called a handshake. So at the beginning of the connection, when you first connect to a web server, for example, you perform a TLS handshake. That's in yellow here. And that's asymmetric cryptography. So you can be sure that you're actually talking to the correct server. And you can be sure no man in the middle can just read what you send to the server and what the server sends to you. So that's all asymmetric crypto. And here comes the problem that I promised. If you look at this guy, I don't think I can make polls. I would be curious if people know who that is. Maybe you can take a guess. That's a smart cookie. There's a guy named Peter Shor, and he came up with an algorithm that destroys all of asymmetric crypto that we use today. Because as it turns out, we have all kinds of different primitives, asymmetric primitives, but they all rely on 2 mathematical problems. That is namely integer factorization and the discrete logarithm problem. So integer factorization is used, for example, by RSA. Maybe you've heard that before. RSA is integer factorization. And things like elliptic curves or Diffie-Hellman use the so-called discrete logarithm. And these are 2 problems that are hard, and that's why these systems are secure, because modern computers can't compute integer factorization and discrete logarithm efficiently enough. But as it turns out, there's a certain type of computer that can solve those 2 problems that our security relies on very efficiently. And this class of computer is called a quantum computer. Maybe if you've heard about quantum computing before. So Shor's algorithm would break all of the cryptography we use today, but it would break it if we would have a large enough quantum computer. If you're interested in how Shor's algorithm works, check out Wikipedia. I mean, we won't have the time during this talk to go into the details, unfortunately, even though it's quite interesting. But you need a little bit of quantum mechanics notation here. You see up the bracket notation. That's a bit confusing in the beginning. Yeah, but Shor's algorithm works. It does work, but it requires a quantum computer large enough to break our cryptography today. If you're interested in the high-level details, there's a very nice YouTube video about it by Veritasium about both quantum cryptography and quantum computers and how Shor's algorithm works. So if you're interested in that, check out the YouTube video. It's quite good. I know people that contributed to the video and they got all the details right. It's a really good video for an introduction. So there's Shor's algorithm, and we'll break all of cryptography that we use today. And as I've said before, our passports, our key fobs, our car keys, our banking cards, our web servers, our instant messengers, everything uses cryptography, right? And all of that would be broken. So the question that arises from that is, okay, when will we have those large quantum computers? Since the algorithm would just break literally everything we use, well, the answer is we don't have a magic 8-ball. We can't really tell. Nobody knows for sure. So the experts have varying opinions. They say some experts say within 5 years. Some experts say it will never happen. The majority of estimates is in the 10 to 15 years in the future, but we honestly don't know. It's still an active field of research. There are quantum computers, but they are too small so far to attack actual real-world instantiations of our cryptography. They can break some small toy examples, but they can't really break the real cryptography yet, unless they become bigger in the future. And companies like IBM and Google are working hard on getting large quantum computers, because large quantum computers would also have other benefits. For example, they could speed up machine learning, some machine learning computations a lot. So there's a big incentive to invest in that kind of research to build large quantum computers. So it's a race against time. If a large quantum computer becomes available, all of our digital communication would be compromised. And that's a problem. So we have to do something about that. And the research community realized that. And even the governments realized that. So already back in 2015, I think, NIST, the US-based standardization organization, launched a call. Because if you need a new primitive, if you need a new cryptographic primitive, usually those primitives are found in so-called crypto competitions. And very often they are launched by NIST. So NIST says, we need new algorithms. In 2015, NIST says, we need new algorithms that withstand quantum computers. We need new primitives, new asymmetric primitives that are quantum secure. And then they say, okay, you have 2 years to submit proposals. We're going to evaluate them, and then we're going to see who comes out victorious out of this competition. But of course, as researchers, we do not want NIST to call the shots and make all the decisions. So NIST is just moderating the process, and in the end, deciding what algorithm gets standardized. But the entire process is really done by cryptographers. So how does that work? Well, ground rule of cryptography is a system has to stay secure even if it falls into enemy hands. So, in other words, a system has to be secure even if it's public knowledge how the system works. So the security of crypto these days should only rely on the secrecy of the key, but not of the secrecy of the algorithm itself. My enemy can know how the algorithm works and still not read my communication. That's important. And during a crypto competition like NISTs, we do that with public scrutiny. So when we want to find a new algorithm as cryptographers, we define this algorithm, we publish it, and then other researchers, other cryptographers and crypto analysts can look at these algorithms, try to break them, see how secure they are. So yeah, modern primitives, modern cryptography primitives rely on two pillars of security. That is, one is security proofs. So if you publish an algorithm, you also publish a security proof for the algorithm, for the primitives, and public scrutiny. And public scrutiny is very important because you might think, okay, so there's a proof, so it has to be secure. Well, no, not really. Very often things do have a security proof, but in the end turn out to be vulnerable nevertheless. So public scrutiny is very important. You publish the algorithm for a couple of years, cryptanalysts can try to break it, and if they manage to break it, the algorithm was not secure. To give you a rough idea, primitives like AES, for example, for encryption, they've been around for decades now, and cryptanalysis hasn't really made progress there. So we now consider AES as secure. It's been around for very long, and nobody found real weaknesses. So you might wonder, does this actually work? I come up with something, I publish it. Who's gonna check? Who's gonna sit down and try to break it? So I brought an example from the post-quantum process mailing list. So this was a Chinese researcher, and he published a new signature primitive based on, or it's quantum secure, so post-quantum signature scheme. And he says, I welcome cryptanalysis on this signature scheme. In this case, you can look at the time stamp above. It took around 3 hours for the first cryptanalyst to break the scheme. So I'm not giving you this as an example to say they did bad work here with the signature scheme. I'm giving you this as an example to show you that, and it is true for all of security, it's very easy to build a system where you are totally convinced it's secure, but as soon as somebody else looks at it, it completely falls apart. So your security should never be based on the assumption that you think it's secure, so it should be secure. You should always have other people look at your code as well, at your stuff as well, because they have another perspective. So here it took 3 hours to break this post-quantum signature scheme. So obviously, it didn't hold to public scrutiny. But if an algorithm holds for years or even decades, we gain trust in this algorithm, in this primitive, and then start using it. So analysts, this Dan Coppersmith, very good cryptanalyst, they look nice and they're nice people if you talk to them at conferences, but they take their job very seriously and they try to break stuff and they do break stuff. And it's good that they do. So this call was launched in 2015 or 16, don't remember. But the US government is really scared of quantum computers, so they want to standardize fast. In 2022, even based on an executive order of the President of the United States. There was another memorandum saying that the US will go post-quantum. It has to be quantum secure. So this is really on the roadmap for a lot of governments, for a lot of large corporations, for a lot of big entities. They take quantum computers as a serious threat, and they want to mitigate this threat. One reason we're in such a hurry, we want post-quantum cryptography right now, is that there are entities in the world, for example, the NSA in the US, that store large amounts of internet traffic right now. Because if they store it now, and then they manage to acquire a large quantum computer in the future, they can just decrypt this communication later. Or they can decrypt all kinds of secrets in the future, just by storing it now and then waiting for a quantum computer to arise. And that's a problem. That's why we need to have post-quantum cryptography, so cryptography that's resilient to quantum computers right now, actually. What is the timeline? Sorry. The NIST competition was announced in 2016. And the first standards, the first draft of the first standard is already out. And standardization is supposed to happen next year, 2024, the first post-quantum schemes that are quantum secure. And then everybody probably has to use them because US companies that deal with the US government will have to use them. And then they will use them. And the US corporations, the big ones like, I don't know, Google and Apple and whatnot, they usually call the shots. If they adopt a technology, everybody else has to as well. So from next year on, post-quantum crypto will probably be rolled out to the masses. Actually, it already is. If you use Google Chrome browser to watch this stream, there is already a chance that you use quantum secure cryptography, post-quantum cryptography, because Google introduced the post-quantum primitive Kyber into Google Chrome, into the browser. And Cloudflare and Google also enabled Kyber on their servers. So actually, around 10 to 15% of the traffic towards Cloudflare, towards Google, is already quantum secure. Because, it's included in Chrome, but they roll out changes like that slowly. So not every Chrome user uses Kyber, this post-quantum primitive already, but a lot of users already do, and more will follow. If you really want to use Kyber from right now, there's a setting in Google Chrome that you can enable it by yourself. So, seems like problem solved. Yes, there was this big threat, quantum computers, scary, but it's under control, right? Because Google and Cloudflare, they already implemented post-quantum crypto. Kyber, this primitive, is actually the winner of the NIST competition, by the way. As it turns out, the problem is not solved. It's not that simple. And that brings me back to the beginning of my presentation. Because I already said computers are everywhere, but I want to reiterate on that because computers are literally everywhere. Like if you ask some random pedestrian on the street, hey, what's a computer? He'll probably point to that thing standing on the desk, the screen. Oh, that's a computer. Well, no. Really, everything is a computer. In my wallet alone, I have 8 computers that I carry with me, right? Those are smart cards. They have like Cortex M0, Cortex M3 processors on them. They do cryptography on the smart card as well. A car is just a computer that happens to drive around, right? My washing machine is just a computer that happens to wash my laundry. A satellite is just a computer that happens to orbit Earth. I mean, these are all computers. Everything. All of them, or almost all of them, pretty much all of them, do use cryptography. So the problem is actually not solved because we have all of these devices, all of these software, legacy software that doesn't use post-quantum crypto as a big, big challenge for them to migrate to post-quantum. So I talked a lot about post-quantum cryptography. What is post-quantum? Post-quantum cryptography is just exactly this type of asymmetric primitive that is secure against the quantum computer. That's post-quantum crypto. When we talk about post-quantum asymmetric primitives, we talk about two things. Either KENs, these are key encapsulation mechanisms. You can use them for key exchange, for example, so that Bob and Alice end up with the same key, but somebody listening to their communication can't know which key that was. Authentication and signatures. There are also post-quantum signatures that you can use to sign something to make it authentic so that somebody that receives the signature knows it was really originating from you. That's what signatures are for. That is post-quantum crypto. It's a lot more diverse than pre-quantum crypto. As we saw earlier, pre-quantum crypto depends on integer factorization and the discrete logarithm problem. These are only two problems. Post-quantum crypto is much more diverse. There are different kinds of mathematical problems that you can use. And the underlying problems, they're roughly divided in 5 sections: hash-based, lattice-based, code-based, multivariate, and isogeny-based. Now, they're all very interesting, but they're also all rather mathematical. So we don't have the time now to go into the deep mathematical aspects of those things, unfortunately. But I want to tell you that post-quantum crypto is mostly lattice-based crypto. So lattice-based crypto is fast and not too big. So most applications in the future will most likely use some sort of lattice-based cryptography. Because in this set, we're going to standardize now. We're going to standardize for primitives, Kyber, which is a key encapsulation mechanism, dilithium, Falcon, and Sphinx Plus. Now, Sphinx Plus is hash-based. The other three are lattice-based. But what does lattice-based even mean? What's a lattice-based post-quantum algorithm? Well, a lattice is this sort of structure, right? Where you have points, for example, in a plane, and they follow some base. If you paid attention in linear algebra class, you will know that if you have a base, so two vectors, you can combine them in all kinds of ways to reach points in a plane. And these points, this set of points here denoted in red, this is the lattice. Lattice, yeah. In a lattice-based crypto on a high level, what we do is we take a secret key just to be one point in this lattice. So one point that you can reach by via linear combinations of these two base vectors. And these two base vectors, the lines here in red, they essentially describe the lattice. So for lattice-based crypto, you have a secret key, which is just a point in the lattice, and you have a matrix that describes this lattice, because the matrix just consists of those two base vectors. What we do then in lattice-based crypto is we add some error, small error, to our secret key. And this small error leads us to another point. This point is not in the lattice, but it's very close to the lattice. And the secret key, as here, the lattice point is our secret key, this public key, so that everybody can know, is this T value. So the point is not on the lattice, but very close to the lattice. That's T, that's our public key. And as it turns out, if I have the public key, this T value, finding the lattice point S that is closest to T is actually a really, really hard problem. It's a problem that classical computers can't solve efficiently, and as we believe, quantum computers also can't solve this problem efficiently. So this is a mathematical problem that we can use, that we can base our primitives on, so it's quantum secure. So, for example, in Kyber, which is the scheme that Google Chrome already uses now, we have a public key, which is a matrix and a vector. That is, matrix is defined, defines this lattice. The T is this point close to a lattice point, and the private key is actually the point, a point in the lattice. Yes, and this is called, this problem of finding this lattice point close to the point that's not on the lattice. This is called the closest vector problem. And as it turns out, this is even an NP-hard problem in the general form. Right? In lattice-based crypto, we use special kind of lattices. So one question is this special kind of lattice, can we solve this problem more efficiently? But so far, it doesn't look like it. So Kyber works like that, with this public key, secret key, lattice point, close to lattice point. And it's going to be standardized now, and it's already in the Chrome browser, and Cloudflare, for example, uses it. It comes in 3 flavors. Google, for example, uses in Chrome, uses the one in the middle, Kyber 768. And these are just different security levels. So the less you trust Kyber, the higher the security level should go. So you have more margin in your security estimates, let's say. So Kyber 512 is like the smallest instantiation of Kyber. It's roughly as hard as breaking AES 128. Kyber 2024 is the hardest one, roughly as difficult as breaking AES 256. So all of these are really fine to use. They're secure enough, even Kyber 512. But if you don't trust Kyber so much yet, because it's a rather new scheme, you can also do it like Google and just use a higher security level, like, for example, Kyber 768. And they have different parameters, N, K, and Q. And as you can see, the different security levels only differentiate themselves, are only differentiated by this K value. What does that mean? Well, Kyber internally works with lattices, but lattices that contain polynomials. And N just gives you the degree of the polynomial that's used within. Now K, Kyber uses lattices and vectors, and K is the size of the vector. So how many polynomials do I have in a vector? And Q is a modulus, as you know, from pre-quantum crypto, that I just reduce the numbers used within Kyber with this modulus. So one problem with post-quantum crypto is that it's large in the sense that the keys are big, because you have to transfer keys, of course. So you can have a comparison between elliptic curve crypto on the left, in the middle is RSA, and on the right is Kyber. So Kyber is larger in the lowest security level. However, If we go to the highest security level, it's 512 or 256-bit AES comparison, we see that elliptic curve is much, much smaller, but RSA and Kyber are actually roughly the same size in the highest security level because RSA keys get very big, very fast. So it's bigger, but it's still manageable. What we also care about, of course, is speed. And here Kyber and lattice-based crypto really shines. So how many cycles, how many processor cycles do you need, for example, to do a private key and a public key operation? And here you can see Kyber is even faster than elliptic curve crypto, and RSA is just super slow. So let's throw out RSA and just look at elliptic curve crypto, and you can see Kyber is much, much faster than elliptic curve crypto, even. Because lattice-based crypto can be optimized quite well, so it's really, really fast. So as it turns out, the highest security level of Kyber is actually faster than the lowest security level of elliptic curve crypto, which says something because elliptic curve crypto is already really, really fast. So in conclusion, why should we care about post-quantum crypto? Well, computers are absolutely everywhere, meaning cryptography is absolutely everywhere. I mean, it opens your doors for you. It unlocks your car for you. It signs your bank transactions for you. It's everywhere. And it would be completely shattered and broken if a large quantum computer were to arise. So we need to do something about that, and we need to do it now. But post-quantum cryptography is large. It's larger than pre-quantum cryptography usually, in most cases. But it's fast. It can be even much faster than pre-quantum cryptography. And it's coming. So if you work somewhere where you don't have post-quantum crypto on the roadmap yet, you can be the hero by introducing it and making sure your organization stays secure also in the future and stays up to date with threats. All right. If you're interested in this topic, I encourage you to go to cryptohack.org. Also, if you're interested in pre-quantum crypto, like elliptic curves, RSA, these sorts of things, CryptoHack is a really nice website for this is CTF website essentially with crypto challenges. So you can go there, find out about the different kinds of primitives and exploit them, CTF style. And they even have post-quantum challenges, mainly for lattice-based stuff. So I urge you to go to CryptoHack and start hacking. All right, thanks for the attention. I don't have a back channel here, so I don't know if there are questions or something, but that concludes the talk. So if you have any questions left, just drop me, either ask here in the chat if that's possible, or drop me an email. Well, that's my email address here. I'm always interested in all kinds of use cases of cryptography, how it's used, how it's misused, how it's properly used. So if you have any questions or remarks, just drop me an email. I'll be happy to answer. Okay. We have time for questions now, but I'm not sure via what channel they would come to me. So are there questions? doesn't seem like it. So I'll check. Wait a second. Let's go to the website. It says offline. There's all right. So, I mean, I can also talk a little bit about cryptography in general until my time is over. Oops. Yeah. Apparently there are no questions. So thanks for attending the talk. Please, if you're a security researcher and you look at code and you see, oh, there's crypto, yeah, that's probably fine. Because it's crypto, people that do crypto know what they're doing. Please don't think that. Very often there are very trivial bugs in code that uses crypto, but also in crypto code itself. So stay safe and see you around.
A broken dreamer is your mind. All the scars that leave them behind. We light the world up now. Let us fire in your eyes. Through the darkness into the night. A broken dreamer is your mind. All the scars that leave them behind. We light the world up now. Let us fire in your eyes. Through the darkness into the night.
Fuck that shit.
darkness into the night. A broken dreamer is your mind. All the scars let's leave them behind. We'll light the world up now, let us fire in your eyes. To the darkness into the night.
No, fuck that shit.